Hello and welcome to lesson 26, which is reflection and mirrors. You're probably all aware of reflection by now. You've done this before, probably in grade 8, and we did a little bit of this in physics 20. But the law of reflection is basically whatever angle a wave strikes a surface, a flat surface, it's going to bounce off at the same angle. If we look at the diagram down here, of course, we see the ray that strikes the mirror is considered the incident ray, and the ray that bounces off is considered the reflected ray. And then a vertical line perpendicular to the surface is considered the normal. You see here that it's 42 degrees between the normal and the incident ray, so it's 42 degrees between the normal and the reflected ray. It's pretty basic stuff. Having said that, probably the most common error is the perception that the angle is between the surface and the ray. So in this case, it's going to be, like 48 degrees would be that angle, which is of course incorrect. Other than that, really, it's pretty straightforward. You can see examples of this if we jump to an applet. All right, if we look here at this example, we can see that as I rotate the mirror, we get the reflected ray. The gray line drawn is of course the normal, and again, direct relationship between the angle at which it strikes and the angle that it bounces off at. Pretty straightforward. Nothing too fancy here. So the question is, how does this get maybe a little bit more difficult or interesting? This is going to be with mirrors that are curved. So there are basically two types of curved mirrors, concave and convex. Concave is curved inwards, convex is curved outwards. So obviously there's a quick look at one. So that's a concave mirror. Often referred to as a converging mirror because light will strike it and then converge at a focal point. We have three dots there. The definition for the three dots, of course, is the center, the focal point, which is actually halfway between the mirror and the center, and what's known as the vertex, which is the point that makes contact on the mirror. The PA, or the primary axis, is just basically a straight line that's drawn through everything. Now, as you read through here and it goes through the basic rules of how to draw a diagram, you basically do two things. If we go to here, we can see the two examples. Any line drawn through the focal point in a straight line, strike the mirror and bounce off in a straight line. Any line that is projected in a straight line off of an object and striking the mirror will bounce through the focal point. That's about all there is to it. Let's take a quick look at that here. Now we have a concave mirror. We've got the red object and the blue image. As I shrink or enlarge, we see that there's a direct relationship. But the key thing is as we move it. Here I am behind the center, or really far away. Object is small. As I approach the center, you'll notice something that happens, which is basically the image is exactly the same size as the object, regardless if if it's tall or short. It doesn't really make a difference. Then as I move towards the focal point, you'll notice it gets way too big until all of a sudden it's gone and the crazy lines show up here. At the focal point, we actually don't have an image. It completely disappears. A good example is that you can imagine looking into a spoon. As you look into a spoon, you can kind of see the upside down image, and then it kind of goes all fuzzy and you don't see anything. Once you move past the focal points, you actually see those yellow lines starting to converge. They're actually converging on an image. And there we have it, the image. So we see there's three kind of distinct areas. Behind the center point, where the image is upside down and smaller. When you hit the center point, then the image is upside down and the same size. Between the center and the focal point, the image is upside down and larger till friggin' huge. At the focal point, no image. And then from the focal point to the mirror surface, we have a larger image that is considered erect or right side up. One other thing that's worth mentioning is that the images that are projected off of a mirror are considered real images. So this is a real image, real image, real image, real, nothing, virtual image. The reason why it's considered a virtual image is it's behind the mirror. We can see the same thing here at this site. Grab the candle, it's a smaller image up until the center point, then it's of equal size, larger image, hit the focal point, and then we see the virtual image on the other side, larger. Let's jump back now to the notes. So the notes go through the details of how to figure this out. It gives you some information here. So classifies things as basically the same, enlarged and diminished or smaller, erect or inverted, so upside down or right side up, and then of course virtual or real. Virtual being projected back, or sorry, virtual being projected behind the mirror, real bouncing off and being produced. The big difference is a real image can be projected onto something. So you could use mirrors to bounce an image onto a flat surface, like a screen, to watch. You can't do that with a virtual image because it's behind the mirror. Unless you're actually going to sit behind the mirror to look at the image, you can't actually see it. The second kind of mirror is a convex mirror. So this is one that kind of curves outwards, also known as like a diverging mirror. A good example of this is when you go into a store and you kind of look up in the corner and you see that security mirror that is there to prevent you from like shoplifting and that kind of stuff. You already kind of know it normally is a normal image, meaning that you see everything right side up and everything looks smaller, so you can see more with that kind of mirror. Kind of gives you some, I guess, perspective on what to expect when we draw the diagrams. Much like the other diagrams where you drew two lines, you do the same thing except it's slightly different. If we pan down through the notes, you'll see an example here. Much like the one before where you drew two lines from the top of the object, you do the same thing. The difference is you draw one straight, which is going to bounce off based on the focal point, but the other one you draw is through the center point. A line aimed at the center of a curved mirror would basically hit in a nice straight line and actually not bounce. Well, it would bounce off, but travels in a straight line still on the other side towards the center. Where those two lines cross, on the other side of the mirror, of course, is where our image is. Always get one kind of image, which is right side up and virtual, and smaller. Let's take a look at that over here. We'll switch our mirror to convex. We're going to grab our object. Now you can see farther away, the object is smaller, but still right side up. And as we move it closer, it starts to get larger, but still it's always smaller, right side up. Doesn't matter. We can see that again somewhere else. Here we have another example with a convex mirror. We take a look at the candle, and again, as we move it forward and back, we can see the image is right side up, but smaller, and of course, a virtual image. Now, there's two ways in which you're going to have to deal with these types of questions. Number one is a diagram, or simply answering questions based on where it's located in a diagram. And the second is with calculations. The mirror equation is what you see here, which is 1 over f is equal to 1 over do plus 1 over di. So Dido, I guess, which actually I think is a musician. Good music too. So f is your focal length, which is half your center point or half your radius. And then your do is the distance to the object, and di is the distance to the image. Key things here are the values. The focal length, positive for concave, negative for convex. The distance, so a positive is in front of the mirror, and negative works out behind the mirror. So that would be like for virtual images. And then positive for height, and negative for height for basically upright or erect and inverted images. We can see here an example of where that equation is being used, 1 over f. Radius is 20 centimeters, so instead of using 20, of course, the focal point is half the radius being at the center point. So it's going to be simply 1 over 10 is equal to 1 over do plus 1 over di. Since the object is 30 centimeters, we know that that's where the do is, and we simply calculate the di from there. We can manipulate the formula and get the answer, of course. Things worth mentioning, of course, in this calculation is you'll notice that both the focal value and the object value are negative numbers, indicating that they're both located behind the mirror. Here we see the magnification equation, which is basically, is the image larger, smaller, the same size? Obviously, a magnification of 2 means it's twice as big. A magnification of 1, it's equal size, and obviously 0.5 would be half the size. Hi over ho, hi-ho, it's off to work I go. Sorry, magnification is equal to hi over ho, so height of your image over the height of the object. That is also equal to negative dido, distance for the image divided by the distance for the object. Here we can see in example 3, using the data from example 2, if you have the di and the do value, and say for example in this case the object that is 5 centimeters tall, you should be able to calculate the height of the image. In this particular case, it's looks like 1.3 centimeters. And that's it. There's not much to it other than that. So what we end up with here in mirrors is 3 key things. Flat mirrors, curved mirrors curving in, concave, curved mirrors curving out, convex, the diagrams associated with all 3. Then of course the calculations involved with curved mirrors. Now, while I could go over several examples here in the notes, really what is best to just do some practice yourself. The equations themselves aren't too difficult if you remember some of the key elements. The first set of those key elements are here with the mirror equation. So in particular, whether you're using a positive or negative value for concave, convex mirrors. Same thing for the distance, and then again, what a positive or negative value means for the image height. Second is the height magnification sign and magnification size. So when working with the magnification equation, much like the mirror equation, positive height is above the axes, negative height is upside down. Magnification sign, so a negative magnification are below the axes, upside down. Positive magnifications are above the axes. And then lastly, numbers greater than 1 means that the object is bigger. Numbers less than 1 are smaller for magnification. And then of course 1 is like no magnification, identical size. Other than those particular values, it's just a matter of practice with those equations. So have at her and good luck.